Hello, I'm now going to talk a bit about the formula at last for entropy, something I've been resisting doing because I want to encourage you to think as much as possible in terms of the properties of entropy, but eventually one does have to know the formula. And without further ado, I will tell you exactly what it is. So suppose we've got a random variable x taking values in a set A, and I'll continue to assume that A is a finite set. And we'll say that we'll write PA for the probability that x equals A. And then the formula is sum of all A and A of PA times the log of 1 over PA. That's sometimes written, in fact, perhaps it's even more often written as minus the sum over all A and A of PA log PA, which is of course the same thing. I prefer this because this one, it sort of looks as though it's negative until you notice that PA is less than 1, so its logarithm is negative. And I just don't want to have to make that little sort of mental, bit like the 19th century is the 1800s sort of mental effort every time I look at the formula. I feel this is more sort of transparent somehow, so that's what I shall use. So what I want to claim, first of all, is that this, if we define entropy like this, then it satisfies all the axioms. So what I'm doing now is a little bit like, it's actually going to be a little bit like constructing the real numbers, because this is a construction of sort of an entropy functional, and then later on I'm going to prove that there is in fact only one entropy functional. So let's just check that it works. So what are the properties we need? We need normalization. So let's just see what happens if x is uniformly distributed on a set of size 2. Then we'll get a half times log of 1 over a half, i.e. half log 2, plus a half log 2, which does indeed equal 1, because all our logs are to base 2. So that's okay. Invariance is completely obviously okay. Remember, that's the one if you've got two random variables that basically have the same distribution, then they have the same entropy. Well, we've defined the entropy just in terms of the probabilities that various different values are taken, so then just in terms of the probability distribution. So that's absolutely clear. What about extensibility? That was the one that says that if you add some extra elements to A but give them a 0 chance of happening, then you don't affect the entropy. So what if I have some 0 probabilities? By the way, I didn't comment that the function x log x tends to 0 as x tends to, sorry, x log 1 over x, I mean, tends to 0 as x tends to 0. So we, by convention, we say, obviously, that it is 0 at 0. So if I've got some 0 probabilities, then this is interpreted to be 0, and that just gives us extensibility immediately. Continuity. Yep, this clearly depends continuously on the probabilities in question. Maximization. Finally, we have something where there's a tiny bit to prove. So let's have a look at, so what I want to prove is that this is maximal when the distribution is uniform on A. So let's assume that A equals n, and let's have a look at this. So we get that, let's have a look at the expression sum A and A, PA log 1 over PA, and we're just going to use the fact that the log function is concave. So by Jensen's inequality, and these PAs are non-negative and add up to 1, so that's a convex combination of those numbers there. So by Jensen's inequality, that is at most log of the sum, or the sort of approach. This is a weighted average of the logs. It's at most a log of the weighted average, so PA times 1 over PA, which equals log n, because PA, that's 1 for each thing, so this is just the size of A, which we're assuming is n. And that equals, so what would we get for the uniform distribution on the set of size A? We'd get the sum over all A in A, so it's n times the probability that we would, for each A, so that's 1 over n, times log of 1 over the probability, that's log of n. So we've got that the entropy of our random variable is at most the entropy of what we would have had if it was uniform, and that's exactly what we wanted to prove to get maximization. So that's that one. And now there's a slightly more to do with additivity. So now I've got two random variables, x and y. Let's suppose that x takes values in A and y takes values in B. And we'll write PA for probability that x equals A, PB, I hope there won't be too much confusion. A and B in theory could intersect and so on, but if I just write a little b, then I'm referring to something in B. So that's a probability that, actually I don't think I'll even need PB for the, now that I think about it. So I'll just put that in brackets, that's not going to be very important. But more important is PAB is the probability that x equals A and y equals B. So with that notation, let's have a look at HXY. So by the definition, or by the formula that we're attempting to show satisfies the axiom, so by definition, if that's how we're defining H, this is the sum over all A and B of PAB log 1 over PAB. And now I'm going to write this. So I want to try and get an entropy of X out of it. So I'm going to sort of peel off the A and put a P of A there, and then sum of B, and then I'll put PAB over PA. And this thing here I'm going to split up because I want a sort of 1 over PAB over PA, in other words, a PA over PA over PAB in there. So it's going to be log of, and I also want a 1 over PA. So we just notice that we've got 1 over PA plus log PA over PAB. We've sort of done everything we wanted to do. So why is that? Just because that is the sum of the logs is a log of the products, and the log of the products is therefore log of 1 over PAB, and we get this 1 over PAB. So let's have a look at these. We've got two terms now. And what's the first term? The first term is a sum over A, PA. Oh, so, well, perhaps I will just, I'll just take these two terms separately. So first term is sum A, PA, sum B, PAB over PA times log 1 over PA. So what is the sum B of PAB over PA? It's the sum of all the probabilities that x equals A and y equals B divided by the probability that x equals A. And so that just is 1, because y has to take some value. So this just works out as h of x. It gives us what the formula tells us entropy of x should be. And the second term is the sum over A, PA, times the sum B, PAB over PA times log PA over PAB. Now, what is PAB over PA? It's the probability that y equals b given x equals a. So this thing here is just, so this is, that thing there is sum a PA h of y given x equals a, and that's just h of y given x by the definition of conditional entropy. And so we've established the additivity axiom as well. So all that's reasonably straightforward. And I just note that at this point we have now finished the proof of the result about paths in a paths of length 3 in a bipartite graph, because that proof that I gave in the last video was conditional on there existing a suitable entropy functional, and now we know that there is one. So now let's just see why it's the only one. But before I do that, actually, there's something I want to mention, which is that when I first defined entropy, I insisted that it was a non-negative function. I wasn't very happy about that, and that's because it seemed to me as though that ought to follow from the axioms without the need for, but I hadn't managed to find a proof of it from the axioms. But I'm very grateful to Sean Aberhart, who watched the video and asked the question, is the non-negativity an axiom or a lemma? So I sort of confessed that I didn't quite know. I sort of felt as though it ought to be a lemma, but hadn't spotted a proof. And then he very kindly supplied me with a proof. So I'm going to start by proving from the axioms that the entropy must be at least 0. So let's take a random variable x, again defined on a finite set A. And what we'll do, we'll start by assuming that there exists an n positive integer such that PA is a multiple, so PA is again the probability that x equals A, is a multiple of n to the minus 1 for every A in A. And now let y be uniformly distributed on the numbers from 1 to n. And let's take a partition of 1 to n with EA having size PA times n for each A in A. And now let's let Z equal A if and only if y is an element of EA. So y is a random number from 1 to n. It'll lie in the set EA with probability PA. So Z has same distribution as X. So by invariance, it has the same entropy as X. Now then, let's have a look at the joint distribution of Y and Z. So I'm going to write the entropy of Y. The first thing I want to comment is that that is the same as the entropy of Y and Z. And that's because there's a bijection between pairs. I mean, we've seen this before, but there's a bijection between elements of y and pairs yz, where z is defined the way it is, because z is a function of y. So again, by invariance, we get that the entropy of y is the entropy of the joint entropy of y and z, and that is the entropy of z plus the entropy of y given z, and for each a, the entropy of y given that z equals a. What do we know about this? We know that that's going to be is the entropy. So if we know that z equals a, we know that y belongs to EA, and that's all we know. It's basically y is uniformly distributed on EA. So it's the entropy of a random variable that's uniform on EA. And we've already proved, and this did not use the positivity, so we've proved that, we have to check that, I'm afraid, but we've proved that the entropy of a uniform random variable increases, and in fact strictly increases, with the size of the set that it's uniform on. So it's at most the entropy of y, because the set EA is at most, has size at most n. So therefore the entropy of y given z is less than or equal to the entropy of y, and that implies by this equation here that the entropy of z is greater than or equal to 0, and the entropy of z was equal to the entropy of x. So that's given us positivity. Now let's get on to the uniqueness of the entropy functional. Now you may remember early on I proved that the entropy of a random variable that's uniformly distributed on a set of size 2 to the k is k. So we've got that. And the proof was that we can just write it as, we can take x to be uniformly distributed on, say, 0, 1, and we take k copies of x. That'll be uniformly distributed on 0, 1 to the k independent copies of x. By additivity, that has entropy k times the entropy of x. By normalization, x had entropy 1. And so we got that the entropy of a uniformly distributed random variable on 0, 1 to the k is k. Now I want to generalize that slightly. So let x be, so this is a lemma, but I'll just won't state the lemma. Let x be, I'll just prove it. So let x be uniformly distributed on a set of size n. Then for any r, if I take n independent copies of x, then it's uniformly distributed on n to the r. So if 2 to the k is less than or equal to n to the r is less than or equal to 2 to the k plus 1, it follows that k is less than or equal to r times the entropy of x is less than or equal to k plus 1. That's because the entropy of the random variable that's uniformly distributed on n to the r by additivity is r times the entropy of a random variable that's just uniformly distributed just on n. So we're looking at the entropy of a uniform distribution on a set of size 2 to the k, which is smaller than the entropy, or at most the entropy of a uniform distribution on a set of size n to the r, which is at most the entropy of a variable that's distributed on a set of uniformly distributed on a set of size 2 to the k plus 1. And we know those two entropies, those are k and k plus 1, which implies that k over r is less than or equal to the entropy of x is less than or equal to k plus 1 over r. But what is this condition 2 to the k less than or equal to n over r less than or equal to 2 to the k plus 1? Let's write that in a different way. So that's the condition is k is less than or equal to r log n is less than or equal to k plus 1. And let's divide everything by r. So if we get that if k over r is less than or equal to log n is less than or equal to k plus 1 over r, then k over r is less than or equal to h of x is less than or equal to k plus 1 over r. And so we can just find some fractions that are very close to log n, and that will prove that hx is very close to log n. We can get that to be arbitrarily close. And so that all that implies that h of x equals log n. So we'd already proved that when n was a power of 2, and now we've got it for all n. And then the last thing I want to do is generalize that to non-uniform distributions. So now let x take values in A, and as ever, the probability that x equals A equals PA. Now, I'd written out quite a complicated proof of this uniqueness in the notes, which I've now got rid of, because I noticed that Sean Aberhart's trick works to give a rather simple proof of this uniqueness as well. So again, we'll say let's first assume that PA is a multiple of n to the minus 1 for all A in A. I'm just getting slightly worried that I forgot to say something a little while ago. So let's just go back to the positivity proof. I did forget to say something. So just here, we deduced that the entropy of Z was greater than or equal to 0, and therefore the entropy of X was greater than or equal to 0. But that was still under the assumption that all the probabilities were multiples of 1 over n. So the last thing to say is, which I forgot to say, is done by continuity. So the probability, the entropy depends continuously on the probabilities, and we've managed to get it when the probabilities are rational, because we can put everything over a common multiple. So we just have to make that little extra remark. So we're going to do the same here. So we first assume that PA is a multiple of n to the minus 1 for all A and A. So let Y and Z be as before. So again, we're going to, Y is uniformly distributed on 1 to n, and we partition into sets where EA has size PAN, and we're done. So now we'll say that then log n equals the entropy of Y, which equals the entropy of Z plus the entropy of Y given Z, which is the entropy of Z plus the sum over all A and A, the probability that Z equals A, which is PA, because that's how it's done. And then the entropy of Y given that Z equals A. And that is H of Z plus the sum A and A PA times the entropy of Y. Now, Z equals A is equivalent to the statement that Y is in EA. And so this random variable, the conditional distribution of Y given that it belongs to EA, is just uniform on EA. We know what to do for uniform distributions now. So A and A, PA, and this will be log of the size of EA. And EA had size PAN. So we're almost there. In fact, just to save myself a line, let's write that log PAN as just log of PA plus log of N. Get rid of those brackets there. And so the sum of A in A times PA is just 1. So it's HZ plus log N, so that's the second term there, and then plus sum A and A, PA, log PA. And now we're done because we get 0 equals HZ plus this. So when we take this over to the other side, we either put a negative sign there or we turn the log PAs into log 1 over PAs. And we get that the entropy of Z is PA log 1 over PA, summed. But I'll write that, so H of Z does indeed equal sum A PA log 1 over PA. And now we're done again by the continuity axiom. And that's the end of the proof of uniqueness and the end of this video.